Welcome to the Foundry by Forge College. Today, we're making a massive leap. We're moving from just designing smart wallets on theoretical paper to actually building the automated quality control factory that proves they work. We've got the blueprints down, so today, let's build the machine that tests the machine.
Here is our roadmap for this explainer. First, moving from blueprint to test lab. Then, the 4 layers of testing. Third, surviving the fuzz test. Fourth, using coverage as a diagnostic tool. And finally, setting up the automated CI bouncer.
All right, Section 1. From blueprint to test lab, moving from theory to practice.
In our last lesson, we mapped out the theoretical decision criteria. Things like session keys and recovery flows. But today, we translate those rules into a physical testing pipeline. We're essentially building a practical factory assembly line to prep for an upcoming security audit. Because, as we all know, auditors demand hard, verifiable proof, not just good intentions.
Section 2. The 4 layers of testing, our quality control assembly line.
Testing isn't just hitting one big run button, right? It's a deliberate, layered sequence. We start with unit testing to check the tiny individual bolts. Then integration testing to see how those assembled gears actually mesh together. Third, fuzz testing, when we aggressively shake the whole machine. And finally, end-to-end testing, when we take the fully assembled wallet out for a realistic test drive. Looking at the specs here, you can see exactly how each test type scales up in both scope and time. Your unit tests, those are lightning-fast logic checks on a single contract. Integration expands to cross-contract flows at a medium speed. Fuzz tests check our invariants at totally variable speeds, depending entirely on how long you let them run. And E2E scenarios use a forked state of the mainnet, which makes them slow but absolutely comprehensive.
Now, before we move past that integration layer, we really need to talk about mocks. When assembling the integration layer, we use simulated external contracts. Think of these as dummy parts that act exactly like live ERC20 tokens or relayers. Why do we do this? Well, so our factory tests never randomly fail just because of external network hiccups. We want deterministic, repeatable results every single time. Moving to Section 3, surviving the fuzz test, chaos on the factory floor.
Fuzz testing is basically feeding absolute randomness directly into your code. It's the software equivalent of shoving a washing machine inside a paint shaker, cranking it to the max setting, and just waiting to see if the door randomly flies open. We're aggressively hunting for those weird edge cases that human engineers might literally never think to write a specific test for.
But in all that chaos, how do we actually know if the system broke? Well, we monitor our invariants. And invariant's an absolute law of physics for our wallet. For example, making sure the total token balance between the wallet and the relayer never magically changes, no matter what random garbage the fuzz test throws at it. Bottom line, if an invariant breaks, you've got a critical bug.
Which brings us to Section 4. Coverage, the diagnostic tool, factory sensors and metrics.
I absolutely love this perspective. As we frequently remind developers over at Forge College, a failing coverage report isn't there to mock you. It's quite literally a diagnostic flashlight pointing directly at the dark corners of the codebase you simply forgot to test. It shows you exactly where vulnerabilities could be hiding. So, what are our actual targets here? For this capstone project, our sensors have to verify a minimum of 85% line coverage. This ensures that the vast majority of our code, literally line by line, is actively being executed and checked by our automated test suite.
Furthermore, we demand at least 70% branch coverage. A branch represents a decision in your code, like a simple if statement. This metric guarantees we're throwing wrenches at both the success paths and the failure paths of our logic. Testing the happy path is easy, right? Testing the error handling, that's where the real engineering happens.
All right, on to Section 5, the automated CI bouncer, gatekeeping the main branch.
Enter the CI gate, or continuous integration gate. I want you to think of this as an unyielding robotic bouncer on your GitHub repository. It ruthlessly rejects any code trying to merge into the main project if it hasn't passed a full inspection. It doesn't care about your feelings, it only cares about the data. To get past this bouncer, your pull request needs the ultimate VIP pass. You must have flawless unit and integration tests. Your fuzz targets, they have to hit their budgets cleanly. Invariants must remain completely intact. Coverage has to sit comfortably above our 85 and 70% mandates. And everything must execute seamlessly via automated scripts. If even one single check fails, you're not getting it.
This entire automated setup ensures we officially stop vibe coding. You know vibe coding? It's just staring at your smart contract, feeling pretty good about it, and hoping it works when deployed. But we're engineers. We don't hope, we verify. We rely entirely on measurable, verifiable engineering signals before making a move.
So your automated factory is humming perfectly. The tests are green, your coverage is fantastic, everything looks absolutely great on paper. But does that actually guarantee your wallet is truly safe from hackers? I want you to really think about that for a second.
Because that provocative question leads us directly into what comes next. In our following explainer, we'll take these exact test artifacts, this solid foundation of automated proof, and hand them over to professional security auditors. That is where we finally find out just how robust our wallet truly is under the intense scrutiny of dedicated experts.
Until then, make sure your coverage is high and your invariants are rock solid. To prepare for that upcoming audit, and to explore even more advanced Web3 engineering concepts, be sure to visit forge.college and continue your learning journey with us. Thanks for joining me on this explainer, and keep building.